Okay, so good afternoon, everyone. Thanks a lot for coming, and welcome again to our webinars, to the webinars of the Commission of Volcanogenic Sediment of IAVSEI. Today we have the pleasure to have Professor Duje Smirčić from the University of Zagreb. He will talk about Middle Triassic volcanism in the External Dinarides and its products. We are recording our webinars as always, so if you have to leave it before the end, or if you know that people that cannot today be here are interested in this kind of topic, please then come to our YouTube channel and can watch again. At the end, we will have, as always, a discussion, so you will be able to take down your questions, and I will be very happy to read the questions to our colleague Duje. Now I will leave him the word, so please, Duje.
Thank you, Andrea, for a nice introduction and presentation of myself. I just want to say that so I'm an assistant professor in the faculty of mining geology and petroleum engineering on the University of Zagreb, and I started my PhD actually working with a sedimentological approach on the volcaniclastic deposits in the Middle Triassic. And this presentation is actually a result of several projects of my PhD and stuff which still is not published from it, but the thing, and a lot of, let's say, several collaborations on different projects which I was working past couple of years, and the results of these projects are going to be presented in this talk. So we're speaking about Middle Triassic volcanism. So everyone who is probably used to more recent stuff is maybe going to be a bit disappointed, but we're quite happy when we find any kind of outcrops and everything is visible, or anything is visible. So we are very, let's say, very fond when we have some of these volcanoclastic stuff preserved in our successions. So mostly of these volcanoclastic deposits are embedded in different kinds of sedimentary rocks. I'm going to try to skip those and just briefly say about them, but just to make a let's say overview of the genesis of these kind of deposits. But I'm not going to go into details about these more sedimentary stuff. So I'm trying to go into focus on the volcanoclastic stuff in the meanwhile. So as I said, yeah, I'm a sedimentologist, and oops, sorry, what's happening? Nothing's happening. What? Oh, yeah. But okay, to get a more closer look at what we are talking about. So this is a bit simplified map from Schmidt et al. At 2020, and here we have the dinarides, which now we see that they are presenting a mountain chain bounded by the Alps on the north, by Hellenes on the south, and by Adriatic Sea, which is separated from the Apennines. And here we have the Pannonian Basin. And in this section, on this actual picture, we see that the entire area here is called the dinarides, but we're going to focus mainly on the external part of the dinarides, which are dominated by thick Mesozoic carbonate successions, originated on the platform, actually in the shallow marine areas, while the internal dinarides, while the internal dinarides are actually presenting the deposits formed on the platform margin and on the deeper parts of the shelf. On top of them, Neotethyan ophiolites are overtrusted. So I won't go into a lot of details because there's a lot of structural geologists who are working on these reconstructions. But just to give you a brief situation of what was happening in the Middle Triassic, so we know these paleogeographic reconstructions by Stampfli and Borel and Van Hinsbergen from more recent years. But what was happening is the opening of the Neotethys Ocean and the subduction of the Paleotethyan lithosphere. In this case, in the case of the Stampfli and Borel reconstruction, the Paleotethys was subducting towards the north, and in this case, it was subducting towards the south, beneath the Greater Adria. But nonetheless, this Greater Adria territory was actually shallow marine, and it was dominated by platform sedimentation, so carbonates. And by the Middle Triassic, it started to disintegrate and formed a complex structure of horst and grabens, forming deeper marine parts or basinal parts, which are then filled with different kinds of sediments, including the volcaniclastics. And this Neotethyan rifting also was accompanied by volcanic activity and the products of what we are going to talk about today. So here is a nice reconstruction of Van Ginsbergen et al. From 2020, and there's a nice animation. If you want to, I can show it later, but now I'm just gonna skip it, not to let's say, to be short and concise at some point, or at least try to be. Well, this section here is actually from Balling et al. 2023, which is showing the formation of today external dinarides. So as we said, the Neotethyan opening started in the Triassic, and these structures are seen in this reconstruction. And these structures from the Middle Triassic served later as inherited structures in the formation of today's dinarides that actually took place in Eoligocene and actually formed the complex fold and thrust belt of the external dinarides. And this is, let's say, the cross section, or typical actually cross section throughout the dinarides. This is presenting here we see the cross section over Velebit Mountains, which is, in my opinion, the most prominent structure in the dinarides. And this is how we look. So how it looks, and we see that mostly we have actually the outcrops of carbonate platform deposits. So Middle Triassic stuff is not so exposed in the entire external dinarides. And this section is very important because here you see one of the most important islands in Adriatic Sea. It's called Premuda. That's the place where I'm originally from, so I have to advertise it a bit. So if you take this look, it's also from the mentioned paper. Here we have several sections across the dinarides, which are presenting a general, or let's say schematic presentation of lithologies from Paleozoic as being the oldest rocks in the external dinarides, and up to the Upper Cretaceous, so end of the carbonate platform deposits. So we see that Paleozoic is composed of clastics and mixed carbonates and clastics, and then we have the lower Triassic stuff, which is dolomites, dolostones actually, and some siliciclastics. And then in this Middle Triassic, we have these brown patches, which are presenting the volcanics and volcaniclastics of the Middle Triassic related to the opening of Neotethys and this geotectonic situation, which I said about a couple of moments before. And on top of them, we have a continuous carbonate deposition all over, boring shallow marine carbonates till the end of Cretaceous mostly. So if we take a look at this map, again, what we saw before, but here, here we have these purple patches, purple areas, where we see Middle Triassic outcrops, and these yellow stars are the locations which we are going to speak about today. And I'm going to try to be, let's say, short, not maybe, but we're going to try to be concise about talking about these locations. So as you see here, not a lot of Middle Triassic stuff, but what we have, I think we did our best to present and to make research on them. So starting with the northwestern Croatia, it's in this area here. It's called Mount Ivančica. It's actually a chain of mountains composed of more or less Triassic successions, but only some parts are, so mostly Triassic is dolostones and limestones, but some of them are volcaniclastics. And now we're speaking about the northern part of the Ivančica mountain, where we found an old quarry, which was excavated at some point for construction purposes. And it's composed of, as they describe it first, as from basalts and basaltic clast types or basaltic breccias. And so what we did, we made a drone scan, we sampled everything as what we could, the different, let's say, lithotypes and facies, and we determined several volcaniclastic facies. So one of them we called the autoclastic basalt breccia, which is characterized by different size and class, very unsorted class of basalts, and the texture of basalts is also quite different. And between them, we have these, often we have this flow type texture, which is indicated by hyaline matrix, in which the plagioclast microlites or microcrystals are arranged in a specific way, or aligned, I would say. Also, in such breccias, or such autoclastic deposits, we have this up to 15 centimeters large limestone clasts, which are sometimes composed of reef building organisms characteristic for Middle Triassic. So this Plexoramea cerebriformis, Elolangaceli autidis, that's typical for Middle Triassic reefs. So meaning we have incorporation of some shallow marine material into the basaltic, let's say, basaltic volcaniclastics. Also, between the basaltic clasts, we have sometimes chlorite as cement, in which we have needle-shaped plagioclasts. And also, what is interesting that in this, also in this basalts, we have clasts of vitroclastic tuffs, which we usually call pietra verde. I will speak about that in a couple of moments. But the thing is, we have clasts of these kind of tuffs in the mafic volcaniclastics. So we also determined the block to lapilli size lithoclastic breccias, which is composed also of basaltic clasts and also clasts of carbonates. And between them, we have mostly, or not mostly, exclusively in this on this picture, volcaniclastic material. So matrix made of very finely grained volcaniclastic material. While in this case, we have between these clasts, we have calcite cement. We observed textures like this, so grading from the lapilli, block to lapilli size lithoclastic breccia to coarse sized ash lithoclastic stuff, with also some epiclastics as in form of carbonate rocks. And these three are a bit different because they are belonging to the determined secondary pyroclastic facies, and two lithotypes are determined in this case. So we have coarse-sized ash crystalloclastic tuffs, in which we have also dark pumice fragments. And then we have fine ash-sized crystalloclastic tuffs and fine ash-sized vitroclastic tuffs, which are often horizontally laminated. And these are actually seen only in these two areas. And what I want to say is that these three, all these purple stuff and green stuff representing the basaltic volcaniclastics or mafic volcaniclastics, whatever you want to call them, and these three are actually acidic or felsic. So these three are a bit different. So what we try to do now is to reconstruct the, let's say, the formation mechanisms of such volcaniclastic deposits in this abandoned quarry. And this picture here represents something that's proposed in this paper published in 2024. So in figure A, we see actually it represents the disintegrated shallow marine area into a complex horse and graben structure that was created by normal faulting. That was a result of the opening of the Neotethyan ocean or the Neotethyan drifting. And then these basalts were fused through these deep-rooted faults on the surface, or actually on the sea bottom, where they started to quench and cool and formed clasts. And these newly formed clasts were then transported by gravity currents down slopes created again by this faulting. And these more proximal clasts are still influenced by lava flow or fluids circulating between the clasts. So that's why you have this flow type matrix and the chloride cement between them, while with the elevation of the from the source, we have finer clasts. They become more rounded, and they're supported by fine-grained volcanic or volcaniclastic matrix, not volcanic but volcaniclastic matrix, or cemented by calcite cement. And then these two, we are actually we determine them as a syneruptive resedimentation of PDC formed by explosive eruptions somewhere from an uncertain source, and that they were actually emplaced in this part and intrabedded between these volcaniclastics, basaltic volcaniclastics, with like gravity or turbidity type resedimentation, let's say, in this kind of deep water environment. And what I wanted to say also that this is dated by argon-argon on plagioclase, and we got ages of 244.5 plus minus 2.8. So to be honest, when we got, I know that some will say that this is a huge discrepancy of plus minus, but we're quite happy when we get any kind of ages using these methods in the Triassic. So this falls into the Anisian, or actually Upper Anisian, and we'll see why is that important actually with the rest of the presentation and how it ends up in our concept all over the Dinarides. So to summarize a bit, these basalts were formed as effusions in the sea environment. They started to quench. This flow texture matrix was actually due to flowing of magma or fluids between the clasts. With annihilation, let's say, become more distal from the source. They are subsequently fragmented and become finer and incorporate limestones, which are also somewhere in the vicinity. We'll see here, and we have this finer grain material between them as matrix, or the calcite cement is precipitated between grades after their deposition. And this is still a bit unknown. So gravity played a crucial role, as always, in sedimentation. Everything is falling, so gravitational mechanisms are crucial for the formation of such deposits, also in this kind of sense. So why am I speaking about the felsic volcanism before? Because in the rest of northwestern Croatia, and that's actually in the entire mountain chain seen here. So we have southern part of Ivanščica Mountains, Strahinščica, and Puna Gora. We recorded and sampled a couple of sections, okay, which are composed dominantly of green vitroclastic and crystalloclastic tuffs. They're composed of fine ash vitroclastics and coarse ash crystalloclastic tuffs. And we also have in these two sections, so in this section we have trachybasalts, and in this section we have trachybasalt hyaloclastite. So everyone, I think, not I think, but I'm sure that even the locals know that these tuffs are called Pietra Verde tuffs. The term was used first in 1916 by Dule Richter Piller, I think, or something from the Southern Alps. And it's common even in the common people, non-geological people. But what I want to say is that here these tuffs are felsic, so acidic, or composed. They have we can see now that they are vitroclastic and composed of very fine vitroclastic material, vitroclastic particles that are plated usually. Here we have a crystal or vitrocrystalloclastic tuffs with some pumice fragments and some plagioclase crystalloclasts. Some pumice fragments can also exceed to lapilli size at some samples. There is often a sharp contact, an irregular and sharp contact between the fine ash vitroclastic tuffs and coarse ash crystalloclastic tuffs. And we actually had luck because these vitroclastic tuffs, although sometimes the transition to the chert is not so clear and visible, but they are interlayered by cherts, by radiolarian cherts, which were sampled and the Radiolarian ages revealed also Illyrian to Passanian age. So this is in accordance with the previous locality. But what here is, in my opinion, interesting that in these three sections, so this section, Kuna Gora, this one, and this, above the Pietra Verde tuff, as we call it, we have dark brown to actually very dark, black even, material, the sediments, which are composed of silt-sized particles and sand-sized particles, so presented here. But these are also, I would say, volcanogenic. So we determine these as secondary volcaniclastic deposits that are composed also of volcanic material, but their, let's say, genesis was a bit different than these ones, than the green ones. So we said that the green ones are a product of explosive volcanic eruptions, as we saw, and then as is characteristic for the entire Middle Triassic in the entire Greater Adria, to be honest. And we determined them as PDCs coming into seawater and then being syneruptively resedimented as let's say, as turbidity currents, forming these kind of segregations of coarse crystalloclastic tuffs from fine vitroclastic tuffs. And these laminations, horizontal laminations and stuff that we saw actually as a turbidity characteristic. So these volcanogenic, I would say, or secondary volcaniclastic deposits are sometimes interlaid or interlaminated by laminas composed almost completely of radiolarians. And this is what helped us date everything as age of Illyrian to Passanian. We said that these could also be resedimented at some point. So this is not clear if they are primary or resedimented from somewhere else. So I'm gonna continue on with the northwestern Croatia, because we're still there's always a question, where is the source material for such volcanic eruptions and stuff like that. But then at some point, walking through the forest, we found outcrops like these, like a 25-meter thick outcrop of something that's very laminar, I would say, or actually exhibits this flow type texture. So this is a rheolitic. We decided to call it pyroclastic density current, and or pyroclastic flow. And we are not, or we are actually, we cannot clearly say that this is a part of deep marine successions, because it's bounded by faults that bring it into contact with Miocene deposits on one side, or Permian to Lower Triassic sandstones on the other side. But it was dated, and this pyroclastic flow actually revealed ages of 243.8 plus minus 0.43 million years ago. And then in Slovenia, actually, on the, I would say, a bit more western part of the External Dinarides, the location is called Kumberg Hill, and this is also, this one is called Margechan. I don't know if the locations are meaning anything to you, because it's hard for me to pronounce their names, but still. So Kumberg Hill in Slovenia, we found outcrops like these, which are presenting actually rhyolitic lava flows, or rhyolitic lava, not pyroclastic lava flow, but rhyolitic lava, which is also in full contact with Upper Triassic carbonates and Upper Oligocene deposits. But this is also dated, and we got these ages, so 242.2 plus minus 1.8 million years ago. So that is now we have the idea to see if this Kumberg Hill felsic lava flows, rhyolites, could have served as a primary source for these kind of pyroclastic deposits, and which is their relation to the stuff we had before as Pietra Verde tuffs in deeper marine succession. So this is around 80 kilometers away, which in my opinion is not a problem for let's say for a pyroclastic flow to reach such distances. But also we have to include the tectonic displacement of these two locations. So this is in preparation, and hopefully it will see the light of day at some point this year. So we're gonna see what you are going to see what's happening with this situation. But there's still some research to do, and we can say that this is the same age, but their let's say clear relations are not still known. So, and what we did then, or actually in 2023, when taking everything into account, this is a bit modified from this paper, but we came up with this kind of model, and we said that this is like these rhyolitic pietra tuffs are interpreted as products of explosive volcanic eruptions and PDCs entering the sea, being resedimented, and then semi-eruptively resedimented, like turbidity currents to deeper marine areas, and distributed with actually with the rest of the pelagic sedimentation by this gravitational currents. These deep-rooted faults served as pathways for basaltic effusions, basaltic magma to come to the sea bottom, being fragmented and actually forming the pyroclastics and resedimented pyroclastics also in deeper marine areas. But laterally, somewhere there was shallow marine areas still existing and producing carbonates, which then also served as a source for these source area for the let's say shedding of the carbonate material to deeper marine areas. And in time of volcanic quiescence, I would say that these areas, let's say after the waning of volcanic pyroclastic activity, these areas could have become reworked or let's say eroded, and actually served as a source for volcanogenic or secondary volcaniclastic siltstones and sandstones, which are also deposited by turbidity currents to the deeper marine areas. So this is the thing what we imagine for the northwestern Croatia. But if we continue on also, going actually a bit more to the west, this is a paper published from Rožić et al. 2024. They have more or less the similar age of volcanics, and why I like volcaniclastics, why I like this this paper is because this reconstruction here. So here, just a brief explanation. They have on top of the Anisian dolomites, so shallow marine sediments deposits, they have the deepening and then occurrence or deposition of tuffs, which are different size. And then they have again, let's say a progradation of platform, then again deepening, platform, and deepening. And these deep episodes are filled with volcaniclastic material. But also they have some peperites, so they have volcanic effusions or basaltic effusions. And why I like it, because they actually are in accordance with our determination that you have actually basaltic effusions in deeper marine areas, while let's say, or in these basinal parts, while on the shoulders of this basin, where you have the volcanic activity producing explosive volcanic activity producing pyroclastic material that is then supplied to this deeper marine areas. So this is also, let's say, this is I would say the westernmost part of the external Dinarides in Slovenia, where you can find the volcanic and volcaniclastic deposits in the external Dinarides. So if we continue a bit more to the south, in Banovina area, we also measure the section that is composed of dominantly of limestone and pyroclastic deposits. Again, these pyroclastic deposits are pietra verde type, so as felsic. You can clearly see the green color here. And these are also composed of or they are presented by coarse crystalloclastic and very fine vitroclastic tuffs. And they're intercalated with pelagic limestones and some radiolarian cherts. And here we got actually abundant and extremely well-preserved radiolarian association, and it revealed also Illyrian to Phasanian age. So in accordance to the things we saw before. So if we move a bit now to the west, it's a small outcrop and not very good looking. So, but what I want to say is here in the Gorski Kota region, we have an occurrence, or actually a recognition of outcrop of hornblenda andesites, as they describe it. And its stratigraphic position is determined based on the relations with the surrounding strata. And what I want to say here that this is the only Middle Triassic outcrop in the region, and this location is called Fujina location. So the outcrops are not so let's say not so nice, but this being the only Middle Triassic outcrop in the region actually indicates that a lot of Middle Triassic is missing. So coming back to the question where the source area can be, we have to include also the erosion equation, erosion variable in the equation. And why is this actually? Why am I saying this? Because when I was doing my PhD, then everyone was asking, okay, but where is no one knows where the material came from, where are the volcanoes and stuff like that. But if we come back a bit to the, let's say, to the reconstruction of what we saw before, this one, and if we can, at least in my opinion, if I can imagine that this is situated in a shallow marine area of these volcanoes, then I can really imagine that the waves from the sea and the tidal currents and everything can, in millions of years, erode such material and then leave just a bit of trace of such volcanic edifice. So we saw also in Hungary that it's not so easy to find a source in these more recent times where outcrops are beautiful, because it's a bit complicated. And if you take 245 million years into the equation, then it actually doesn't. Now I'm not so worried about the question about the source of this kind of material, but still the question is open, of course. And if we find it, we're going to be lucky. So moving a bit more to the south, this is, I would say, this is the northern West Velebit Mountains. We also have a large body composed of andesites and blocks of basalts. Here we can see a huge block of basalt in the mostly andesitic, actually body of andesites and andesitic hyaloclastics. And this also here they're including carbonate clasts. And this is geochemically very similar to this area. So this is also the only, let's say, the only area where Middle Triassic outcrops are occurring in this part of North Velebit. And this, on top of these rocks, we can find Upper Triassic clastics, red clastics as we call it, or Rabel in the Austrian, I would say, terminology. And these clastics are composed of volcanic and carbonate clasts. So I'm saying this because these Upper Triassic clastics are actually evidence that these volcanics and volcaniclastics was eroded and actually finally were supplied to the basinal area till the point the basins were filled actually. Also in this area we can find, or actually in this area we can find these pillow forms or pillow basalts also. Not very often. Usually they are very hideous and very not good looking, but these forms can be found at some locations. So if we continue more to the south again, in the central Velebit Mountains in Lika, This is the place where I did my PhD research, and there's a couple of things I will show you here. But the thing is, this is the first location called the Jovanović Draga. Doesn't mean much to you, but the thing is, this is a hill composed of this pillow basalts, pillow olivine basalts, actually in the middle of the hill, and on the edges, or actually towards the edges of the hill, you have this kind of lithology. So you have clasts of basalts that are supported by finely grained volcaniclastic material again. So we determined that this is, as we call it, coherent facies, and here we have hyaloclastic facies. And in these hyaloclastics, there's a lot of glass shards in this part, and then at some point the limestone clasts come into play. But what I also want to emphasize that on the very edge of this hill, we have let's say a meter thick layer of, again, acidic vitroclastic tuff. So again, vitroclastic tuff in contact with the basaltic, with the mafic volcaniclastics. Here, I want to show you only some thin section photographs of this lithology. So we have pyroxene phenocrystals, which are often have these sieve textures. We have basalt clast and this finely grained material, but here we see a lot of glass shards, and these glass shards have these kind of oval shapes. These oval shapes actually indicate that they are formed from volatile rich eruptions, I would say. So these basalt clasts have different kind of textures, and also we have in between the basalt clasts, I think in this picture it's seen very nicely, that you have this flow type texture or flow type matrix actually between the clasts, where crystal clasts of pyroxenes are included, but also pyroxenes are present in the basalt clasts. And you can see here that the zoning of these pyroxene crystals is a bit different. Here we have lighter and darker, lighter in the core and darker in the rim, and here we have darker and lighter. So darker in core, lighter in the rim. So that would mean that this sieve texture is actually an indication of partial melting and regrowth of pyroxene crystals, and these different kind of zonations would indicate that the pyroxenes were crystallizing in different PT conditions. So that would indicate fast, actually, magma ascent and cooling. So that's why I came up with this kind of sketch, very simplified. So the magma was ascending through the carbonate rocks, which became fragmented, allowed some water to come into the system, forming actually helping the production of vitroclasts with these oval shapes or bubbles, I would call them. And then this basaltic magma starts to fragment in contact with seawater and form hyaloclastics on the let's say on the edges, which are transported again downwards from the uplifted hill at this point towards the deeper part of the basin. So yeah, definitely. And what I forgot. And then again, we have the vitroclastic tuff of acidic composition, which is probably different source area from this. So we're continuing again in this area where we recorded a section in which we determined several facies, and they are all at some point related to volcanic or volcanic activity or volcaniclastic, let's say, products. So from the base to top, we have fleece-like facies, carbonate shell facies, PDCs, I would say again, semi-rapidly resedimented, platy limestones with pyroclastics, limestone breccias, and then on top, on the very top, we have slumped limestones and pyroclastics. So I'm just gonna jump through these through their characteristics just to show you. So this is the fleece-like facies, which is composed of this felsic material, I would say shaly, and up to 15 centimeters thick sandstones, which sometimes are horizontally laminated and exhibit normal grading. And we determine these sandstones as feldspar or lithic greywackers. And the lithic fragments are mostly basalts and andesites. So this being like a fleece-like facies, and this actually similar lithologies are also recorded in the southern part of the Dinarides in the Montenegro, and they call it Anisian fleece in some older, let's say, literature. So if you find something like this, you'll probably Anisian fleece is not fleece in the orogenic sense, I would say, just fleece-like. So these were formed also by gravitational processes, so turbidity currents, and we can say that this volcanogenic or these sandstones are composed of volcanogenic material. So they have the source in the volcanic rocks. And as I determined it back then, I said that this was formed in the time of pause of volcanic activity, and something. So these volcanic source was eroded or reworked, and this actually presents a more, let's say, siliciclastic sediment in that sense, not the primary volcaniclastic material. I'm just gonna jump quickly through this because this is called carbonate shale. It's a boring carbonate, more or less, with this shaly texture, a lot of pelagic fossils. But what I want to say here is that at some point in this entire interval, we have some layers, or actually one layer of crystalloclastic, or this first pyroclastic material, I would say. So it's composed of hypidiomorphic to even idiomorphic plagioclast, crystalloclast, and cemented by calcite. So this would actually mean that the volcanic activity started at this point. And then moving on to the really volcanoclastic facies, which we determined as PDC, or syneruptively resedimented PDC, again into water, which is composed of meter-thick crystalloclastic layers with almost idiomorphic crystalloclasts of plagioclast and sanidine, very well sorted. There's also some biotite in it, but they're usually actually delaminated and plastically deformed. There's also some andesite lithoclasts. So this is the crystalloclastic lithotype presented here, and then we have vitroclastic lithotype, which is composed of very, very fine vitroclasts, glass shards, which are barely visible at some points, but they are usually horizontally laminated. And when you see it, it's really looking like glass. You can cut yourself on it. It's really, really glassy and very, let's say, parts are very, very homogeneous. So we said that this is also a PDC entered into water. Then in these processes, actually, when in the process of incorporating water in it, this material got segregated. So this crystalloclast, more coarser material, got segregated from the finer material of these vitroclastic dust, of vitroclast actually. So moving on to the next facies, which we call platy limestones with pyroclastics. So these are platy limestones. They are often silicified, different kinds of limestones. But what I want to emphasize here is that here we found, at least to me, it was the first time I saw something like this. Accretionary lapilli, which is composed. So this one is found in limestone layer, composed totally of glass shards, of very fine glass shards, with this coarser crystalline calcite core, I would say. But also these layers between the pyroclastic layers between, which are going to be maybe better seen later, but you can see this layer here, and these particles a bit bigger, up to a centimeter big. They are also accretionary lapilli. Here you see contact between the two of them, and the matrix composed of very finely grained volcaniclastic material. So what we said that happened in this species was that we had some shedding from the shallow marine carbonate detritus, which formed limestones like this with lithoclastic limestones. And then we have ongoing volcanic activity that produced these kind of lapillis, which are indication of subaerial eruptions or by surge products. So the thing is, are they, let's say, primary, or are they very deposited? Because till recently I thought that accretionary lapilli are very fragile, but and then they cannot withstand let's say molesting with time and redeposition and transport and everything. But then in Hungary, hearing colleagues speak about it, I learned that they can really be tough if they are actually formed in a pyroclastic surge, and then they keep rolling and grow. And if this is the case, and they are a product of the surge, that will probably mean that they are the source of this material was a bit let's say proximal. It's more proximal than we estimated from the stuff from northwestern Croatia, where we have only let's say more finer material. So this is another facies, limestone breccias, composed of very unsorted clasts, interpreted as debris flows. But what I wanted to show here, that here we have this limestone breccia interval, and on top of them we have this pyroclastics, and then platy limestones, and then again breccia, and then this is repeated a couple of times. So I would say that these debris flows were generated by tectonic activity that formed actually the material, that helped the material slip down the slope, forming debris. And then this also was, this tectonic activity was also accompanied by volcanism, and then produced volcanic or volcaniclastic deposits like this. So the one from this one is actually from this kind of intrabedded with limestones, and again here with limestone. And then on top we have the facies that we determine as slumped limestones, pyroclastics and cherts. And they're really everything, the packages are totally slumped. This is their main feature, this slumping texture. But what I want to say here is that here, actually, for the first time, we have quartz crystalloclast. So very, I would say, very acidic, clearly acidic. The quartz is sometimes rounded, very, very different shape. We also have plagioclasts and a lot of shards, but this here, we don't see the clear, let's say, segregation of vitroclastics, or we have some vitroclastic layers, but we have more, let's say, compound layers with coarser and fine material in one sample. And also here we have what we saw in this layer. This is limestone, but this part here is a lamina we see here, composed, and maybe it's better to see better visible here. So we have cross lamination, but it's composed of fragmented accretional lapilli, which are found in limestones. So again, a question arises: are these and the ones from before? Okay, then they withstand the transport and not be fragmented, or actually why are these fragmented and the ones before are not? So this is a question which is going to be answered hopefully soon. And on the very top of this section, called Donje Pazarište, we found this kind of lithology, which is again acidic. So we have quartz crystalloclasts, and we determined that it's crystallovitric tuff. We also have some pumice here, and in this pumice we have sometimes included quartz in these pumice forms. So these are clearly not, let's say, segregated. So this is composed of also crystalloclasts and vitroclasts in general, totally in, let's say, in one sample. So could this really be a primary PDC? That's how we determined it, that it is. And sadly, the contact between this lithology and below is covered, so we don't. There's lacking, or there's a lack of section, I would say, and then we're not clear about their, let's say, position of replacement, if this is a real PVC. But we still think it is, because we also saw similar lithology 15 kilometers southeast from this lithology. We found it here, mineralogically and structurally very similar. Again, we have pumice fragments which are sometimes squeezed by quartz crystalloclasts, and these are in place, or actually in a near contact, not again clearly visible, but they are in contact with shallow marine limestones with green algae and limestone breccias with reddish matrix. So can this be a part of a PDC placed in a shallow water? And then this, from the last slide, it can also present the same unit. It's still to find out by some more advanced geological technique, geochemical techniques, which we hopefully will achieve at some point. So to summarize this location from the center of Velebit Mountains. So what we see here is that there was some pre-existing volcanic rocks that served as a source for the creation of fleece-like sediments due to this volcanogenic material in the sandstones. And this was probably in times of volcanic quiescence, or let's say at least pyroclastic activity was not pronounced in this time. And when carbonate shells started to deposit in the pelagic environment, then we have a start of volcanic activity, which then grew with the PDC, or sine-rapid resedimentation of PDCs, forming this yellow facies. So the material was produced by PDC, generated on the shallow marine, entering the sea, and then transported to deeper marine areas as more like turbidity currents than a PDC on land. And then again we have tectonic activity, which is producing limestone breccias or debris flows, and we have some shedding from the platform, from the shallow marine. We have shedding with these plating limestones, and then this green stuff is the thing that we are thinking, or we were thinking back then, that this is a unit of PDC which was placed in a shallow marine, and then their relation, it's not dated, so we cannot relate everything to the numbers, because we don't have numbers from these volcaniclastics, but we're gonna try and see if the geochemical analysis will show us their relations. And the very top, what I want to say, the very top is acidic, and we are sure that we had subaerial volcanic activity, because we have accretionary lapilli which are not produced by in any different environment, at least I say, at least I know like that. So if there's any, I would appreciate if you tell me something differently. So we're moving a bit more to the south. This is on the territory of Bosnia and Herzegovina. It's very near also to the Croatian border. Here is a nice example of pepperites. We also here we made a section, and the section is composed of limestone fluidal pepperites, which we see here in the outcrops, and here in the hand sample, and here we see this greenish hyaline magma domain, I would say, or lava domain, and here these parts are actually rounded clasts, or I would say domains of limestones, which are pelagic. In some, I think on on the invitation for this talk, I have a picture of a contact of this class with the hyaline matrix, where you can see actually the orientation of the filaments of the thin shell bivalves in contact with the magmatic domain, with lava domain. So we had luck that these pepperites actually also produced conodons, and they were dated as lower and upper Illyrian. So again, Middle Triassic or upper Anisian. And what we also have here, that here again we have crystalloclastic tuff, and then above we have hyaloclastics. So in situ hyaloclastics and resedimented hyaloclastics, and on top, breccia conglomerate, or as we call it, with volcanic matrix, or breccia conglomerate pepperite. And what I want to say that this crystalloclastic tuff is composed of albite crystalloclasts and pumice fragments. So if we take a look at this picture, here we have a nice example of an in situ hyaloclastic of basaltic composition, or as we will see later on, it's andesito-basaltic. But you see these blocky clasts, which are showing very nice fitting to each other, as we call it jigsaw fitting. So this is determined as in situ hyaloclastic, but when it comes, well, let's say, more distal from the main basaltic effusion, it becomes resedimented. These clasts have, let's say, more space to move, and then they become rounder, and between them we have small, finer grained volcaniclastic matrix. And here they're becoming more and more actually finer, and they incorporate some limestone clasts as well. And on top, we have this breccia conglomerate pepperite. We call it pepperite because the matrix between the clasts is mostly hyaline. It's mostly very, very fine. Actually, it has like a hyaline matrix from the volcanic rocks. So it's composed of clasts of basalts, cherts, and limestones. But on the very top, basalts are actually lacking, and the prevalence of limestones and cherts is seen on the very top of the section, but still in a volcanic matrix. And this is the part which also again made me a bit let's say dubious, because here we have a crystalloclastic tuff, as we see. Maybe the picture is not the best, but here you see these kind of forms. These are pumice fragments, and here you see that they are aligned. They are aligned. I won't say they're fiame, but they look like fiame, and it's composed of acidic minerals, so quartz and plagioclase. So again, we have basalts and again quartz, but if this is fiame, then it's a bit strange that it's how is it welded in this kind of environment. So this is still to be, let's say, to show the relation between this and the stuff which we have in acidic composition in the vicinity. So I read some literature, and I'm going to speak about it now. But this is a bit dubious in my opinion. But I'm gonna show it in a minute. So this is this is intermediate, but it has over 70% of quartz. So over 63% of quartz. So it's definitely acidic actually. But so can it be a pyroclastic flow? We're gonna see now, because at some point I made also this kind of model, this kind of simplified sketch, showing that actually the magma was coming to the surface, being mingled and mixed with the unconsolidated and water-saturated limestones forming peperites. And then, as I found in the McPhee et al. Handbook from '93, there they said that some pyroclastic flows can form directly from vents by upwelling or overflow or low fountaining of pyroclastic glass mixtures, and that some pumice pyroclastic flows and scoria and ash flows are formed in this way. So I didn't know better anything more let's say more clever. So I said, okay, this can maybe work, forming this kind of stuff in the, let's say, this low fountaining gas flow, producing these pyroclasts. And then when the magma is coming to the sea bottom, it gets fragmented, the in situ material stays closer, the resedimented becomes, let's say, resedimented from more to more distal parts of the effusion, and then forming this resedimented hyaloplastics. And then at the end, or the most distal part is composed of this clasts of carbonates and cherts from the probably uplifted areas somewhere in the vicinity, but the lava gases are still flowing and then mixing with between the clasts and forming this pepperite kind of patient. So now we're continuing a bit more to the south, and we're gonna. The time is, sorry for the time, but I hate silence. So this is in near Sin on Svilaj mountain. The location is called Zelovo, and this is a very well-known location, I would say. It's the only outcrop again of the Middle Triassic in this area, and it's studied from the early 20th century. There's a lot of research done already, but what I want to say that this is a section I made during my PhD, and this is a section presented in Gorichan et al. In 2025. And what I can say that the section here with pyroclastics is composed of dolostones and limestones, which are silicified, and then crystallovitroclastic tuffs, and then these clay tuffs, as I call them. And then they're characterized by these slump textures also. We have some horizontal lamination, and we have some cross lamination also in these layers. And we have also brachiopods, which are presented in the paper of Halamsky in 2016. We have ammonoids determined from this location, from the Svilaj mountain, also Middle Triassic from Balini. We have radiolarians from the 225 paper from Gorichan, and we also have some plant debris in the sections here. And this section here should actually present, or actually, this is the older section, and this is the younger section. So this here is dated as Ladinian, early Ladinian. So this should be also early Ladinian or Late Anisian. So in accordance with everything that we already saw. But what is different here actually, that here these tuff layers are maximum 2 meters thick, and we saw before that they are meters and meters thick. In northwestern Croatia, we have 40 meters of green tuffs, of Pietra Verde tuffs. So this is a bit different, and this is the very distinct layer, or very clearly visible layer on the main horizon of this Pietra Verde tuff in this location. So this is a nice reconstruction by Gorichan et al. Because as I mentioned before, all the papers, so Balini et al. They determined a new ammonoid genus from these locations. So there's new brachiopod species. There's a very low diversity of radiolarians in this section. There is a plant debris which indicates some income from the land and erosion from land. So everything is actually indicating a very specific environment that we propose here in the paper from Gorichan et al. 2025, that it's a intra-platform basin, which is formed, let's say, has limited connectivity with the open marine. So everything that we had before was probably a place of this somewhere in the open marine area, and this Svilaya mountain part is a bit more closed. And what I want to say also here, these limestones where we see slumping are very dark and very smelly when they smell of organic matter. So that also makes sense that this was very organic rich, and the organic material was, let's say, possible to stay in this kind of basin. And also, as we determined as crystal or vitroclastic tuffs, so being mixed crystals and vitroclastics, maybe the idea goes in favor of this, that the turbidity currents couldn't have actually developed in these kind of, let's say, enclosed basins. And so moving a bit to the Adriatic Sea, this is a paper from Velikonja et al. 223, where they dated the occurrences, the outcrops of Middle Triassic volcanic islands. So we have Vis Island, where they actually have a small outcrop of altered basalts, but we also have these small islands near Vis, which are called Brusnik and Jabuka, which are determined as Gabbro. And what I want to say actually that they dated it, and the ages here are 227 plus minus 5, and for Jabuka, and 221 plus minus 0.5 plus minus 2.5. So this is interpreted in the paper that it's probably Carnian or early Norian, so upper Triassic, but they still, let's say, they still say that it can be a bit older. But if this is Carnian or Norian, then this should be the, let's say, the last volcanic episode, or actually the end of the volcanic episode in the External Dinarides. So now a bit more of let's say of geochemistry, just to show a quick overview. Why am I showing this? Because these are determinations of type of rocks. So we have, I just want to show you that we have, they're supported by these diagrams, that we have basalts, we have andesitic basalts, andesites, and rhyolites as effusive rocks, and as volcaniclastic rocks, we have basaltic hyaloclastics, basaltic andesitic hyaloclastic, we have some intermediate tuffs, we have acidic Pietra Verde tuffs, and we have some volcanogenic sandstones and siltstones also in our studied successions. So now this is a summary of all the, let's say, proposed models, which showed that everything took place in a deeper marine area. It was adjacent to or very close to the shallow marine areas that actually also served as a source for carbonic materials. So gravity currents played a crucial role, actually forming turbidity or debris, turbidity currents or debris currents. We have seen eruptive risk sedimentations of PVC entering the water. We are pretty sure that we have sub-area volcanic activity. The quenching of basalts happened in the deeper marine areas, and we have some magma sediment interactions, so in the unconsolidated sediments, and we have also reworking, redeposition, erosion, whatever we want to call it. We have them included in the let's say in the northwestern Croatia of the in this volcanogenic species, as we called it. So to summarize the ages, this is a nice sketch done by my dear colleague Duje Smirčić, which I stole for this presentation, and showing that all of these successions we dated by radiometric methods or by biostratigraphic methods. They all fall into the age of Late Anisian, Tertiary, and Ladinian, and this in the same time we have acidic and basic volcanism, so or mafic or felsic, whatever we want to call it. So we have bimodal volcanism, and we have the oldest Neotethyan crust presented in the paper of Kukoč et al. 2024, which actually suggests that the beginning was in the Late Anisian, and I'm going to show a bit more of the diagrams indicating that. And this volcanic activity continues till the Norian, according to the paper of 23. So from the intrusive bodies, but still, volcanism was active till the Norian in this place. So these are the geochemical characteristics, and I won't actually talk about them a lot. But what I want to show that we can clearly see that they more or less have very similar patterns of these rare diagrams and incompatible elements. And this here is a bit different. This is the paper I mentioned before, Kukoc et al. 224, indicating that the analyzed basalts from the ophiolites are a bit more E-morb-like. So they're very close to the E-morb average. So this should actually indicate the beginning of the ocean, of the opening of the Neotethys ocean. And again, if we take a look at some more diagrams and see here, then we can see that all these fall into the area of D. D meaning, if you take a look at here, the continental arc basalts. So D is, if they are, and they are actually, magmas are determined as calc-alkaline, so related to subduction in the, let's say, in the geotectonic sense. But this from the paper of Kukoc from 22-24, these fall into the B part. So these are actually the E-morb part of the, sorry, see here, E-morb part of the diagram. So there was also a question of the relation of the calc-alkaline magma to the subduction, let's say magma that is generally formed in the subduction areas, and Neotethyan rifting. So this was a question where how to correlate these, or how to explain the subduction type magma in the rifting stage. And then these are some papers published from Slovenec et al. From 2022 and 23. And if we take again this closer look at these paleogeographic reconstructions, we can see that here we have also a subduction of the Paleotethyan lithosphere. And here we have, as they call it, as Van Gisbergen calls it, Balkan Paleotethys subduction beneath the Greater Adria. But what I want to say, that we determine, or actually we interpret this, that the Hercynian Paleotethys actually played an important role in the subduction of the Hercynian Paleotethys, or let's say inherited Hercynian structures played an important role in the formation of this kind of magma, because they got metasomatized and then partly melted and formed, and also it included melting of the continental crust and formed, let's say, an unusual magma for this kind of geotectonic stool. So actually, what I wanted to say that the geochemical composition of volcanic and volcaniclastics is largely inherited from the older, let's say, arc-related lithologies related to the subduction of the Paleotethys, which was affected by partial melting, and meaning that the present chemistry, indicating actually the existence of the arc, does not imply the real volcanogenic, the actual tectonomagmatic environment of the formation of the presented rocks in this study. So a couple of processes were actually involved. So forming the magma, the subduction of juvenile material, the subducted continental material, so continental contamination, and also the subduction of oil-like mantle from these kind of environments, or these kind of situations. And what also I want to show here This is the paper from Slovenec et al. 2023 from ophiolites, which I mentioned before also at on some slide. But here they measured neodymium isotopes, and you can clearly see the increase of increase of continental contamination following the sections. These are the sections which I already presented. And here you can see the increase of continental crust in the formation of magma. So that also comes into, let's say, fits well into this interpretation. And then let's say, to summarize everything, I'm not sure what's happening. The computer had enough. So this is more or less what I want to say in the complete summary. So the Middle Triassic volcanic activity in the Dinarides is related to the Neotethyan rift. It occurred it started in the Late Anisian and continued towards the Ladinian. The material, or actually the volcaniclastic deposits, were formed or actually emplaced or deposited in basins or grabens or half grabens, along with different kind of lithologies. These deep-rooted faults that were formed by normal faulting related to the rifting served as pathways for the mafic magma. But also we have bimodal volcanism or bimodal volcanic activity that produced also felsic magma, or actually are related to the source for the Pietra Verde type pyroclastics that were in place by a combination of subaerial explosive events, PDCs, and their syneruptive resedimentation in the newly formed basins, which can be enclosed, we saw in the area of Svilaj Mountains, or open as in the entire rest of the external dinarides. And these external tectonics ceased actually or stopped in the Ladinian, as these basins are filled with clastics, again volcanogenic clastics. These we call red clastics or ribald formation. I don't know, that's a common name used in the Austrian terminology, I think. And after the fill up, these basins, which were short-lived, were actually became flat, and then the transgression above them actually produced again, or actually started the carbonate deposition, which is seen as the deposition of the main dolomite, or Dolomia Principale, or Cap Dolomite, all over the places. But still, some basins of the Greater Adria margin still did remain deep. For example, the Bosnian basin or the Slovenian basin, throughout the entire Mesozoic, where you actually can see the pelagic sedimentation all the way till Cretaceous, to the upper Cretaceous. But in the external dinarides, it's not the case. Everything was closed, more or less. So this is it, and thanks for your patience, because I just see that the time is clicking 1 hour and something. So I'm sorry for being such a long-lasting presenter in this today. Sorry, but it was a pleasure talking to you.
Thank you, Duje. It was a very good talk. Yes, it was a little bit long, but was very good.
Sorry, I didn't watch the clock. Yeah.
Don't worry. You present like a review of the Middle Triassic stuff of all the dinarides, and this was very, very good. It was very, very nice. And there are a couple of questions. Let's see. So can you please show your
presentation?
Yeah, the presentation.
Okay.
Let's start with that on the chart. Let's go in order. There are three main questions. The first one is, we can see the presentation. The first one by Mansouri Adil, quite long to me, sorry, Mansouri. The question was, I have a question regarding the litho chart of Bruvno in the green color. Why an unconformity mark, while other charts was not? Thank you. So I think at the beginning of your presentations.
Oh, here it is. Sorry. So
this one,
the
yeah.
question is, sorry,
Why? Well, the
why do we
question
have
is
the
why an
unconformity?
unconformity mark the green color while other charts was not. I think why do you have the unconformities there?
Here, I mean, okay, so because there's really a missing piece between the lower Cretaceous and the Aptian and Albian is marked by immersion, by a hiatus.
Okay.
So this is it's not visible everywhere, but it is seen also around the Dinarides. In Istria, for example, you also have this kind of missing part. But speaking about Bruna is a special kind of, let's say, special kind of structure, because here it's clearly visible that even in the Triassic times it was different than all the other sections. And some interpretations were that this was a barrier that served that, especially if you look at this. So this is the Permian. So even before the Triassic in the Paleozoic, it could have served as a barrier, not allowing the siliciclastic material to come to the let's say to the basin, to the depot area, because south of it we have evaporites, and north of it we don't have. So Bruna is really a special kind of a structure in the Dinarides.
Okay. Thank you. So second question, I was going to ask, this was Rebecca that went away. Have you observed the impact of volcanic incursion, PDC entering deep marine or basalt on the carbonate system or marine environment?
Yeah, it's I think that's I was always thinking it's when you have an income of material, then you have or I don't know, siliciclastic, whatever clastic material to the sea, to the carbonate system, then I would think that it's killing the carbonate production.
Okay.
But I found a paper from Vorosh speaking about that this also, but okay, just to rewind a bit. The thing is also the siliciclastic input in the sea environment can also help boost some life. I know, for example, radiolarians are very abundant in these kind of circumstances because they are blossoming. There's a lot of nutrients. They are very happy. They grow. They diverse. They evolve and stuff like that. Also, a paper from Vorosh, I think from 2008, is saying that the Ladinian volcanism also helped the productivity of ammonoids. So he called it also fertilization of the ocean.
Okay.
So I would say and we saw here that you have carbonates. You have carbonate clasts from the shallow marine, from the reefs, coming to the deeper areas, but there's still some production. You see clearly these reef organisms in these clusters. So I would say that the volcanic activity did not influence much the carbonate production, but in why, to be honest, I'm really not sure. But the thing is, it didn't play a crucial role in the production of in the stopping of production of carbonate deposits. Hi. Everyone left, huh? Okay. Hey. Ciao, ciao, Andrea. I cannot hear you, but still.
Were you able to? I don't know what happened to my connection.
I think I killed it. I killed it with my talk.
Okay.
Yeah, probably.
No, don't worry. There was a couple of questions more.
Yeah, definitely. Shoot.
Okay. The volcanic activity then was related to the subduction, right?
It was, yeah, it's complex, but it was related to the subduction. So we think that these products are related to the opening of the Neotethys.
Okay.
But the thing is, of course, if you have an opening somewhere, then you have a subduction somewhere. I don't know. I imagine this kind of environment quite similar to today's, let's say, East Africa rift.
Yeah, it's quite a complicated question about the formation of magma during the Tethys. That's right.
It's, I think we can speak for hours about it, but yeah, it is related to the subduction and it's related to the rifting. So I think that's the most clearest question I can say at this point, because yeah, it's a bit more. I don't know who asked the question. If you want to, I can send you some papers on it, and then
yeah, maybe it could be a good.
So yeah, but it's not so. Yeah, it's always a problem to say where the subduction is starting and the rifting is. If you take a look on the map of now of geotectonic or the boundaries between the continents, and you take a look of the Eastern Africa rift, then you can see that there is also rifting and subduction, and then you see continental rifting, ocean rifting. Where is one starting and the other
yeah,
stopping?
it's complicated. Okay.
It's not so. Yeah.
And I suppose that you already speak about the relationship between volcanic activity and effect on the ecosystem, right? Because I lost this.
Yeah, I think so. I think I said, but yeah. To be honest, we didn't see any influence on the carbonate on the stopping of carbonate production because we clearly have some reef building organisms in vicinity and above actually all around these basins we have these dolostones, entire area of dolostones or limestones.
Okay.
So I don't see anything special happening there.
Okay, last question by Wildan. Okay, Marta said it would be great if you can send her some papers. Then the last question by Wildan is there any possibility of petroleum system development in your study?
Great question. That was also my opinion when I was doing my PhD, because I was thinking these basins were a bit confined, and maybe they can hold a bit of organic matter and stuff like that. But the thing is, I did some organic matter measurements, and we saw that everything is burnt. Everything is too hot.
Okay.
So I think we weren't lucky. But in this paper of Goric and et al. 225, so the last which I was speaking for this confined basin, this enclosed basin, you have a lot of organic matter in there, and they did some organic geochemistry, but it's burnt and it's not so. It doesn't serve like a source for the carbon for
source rock.
oil. Yeah. I guess.
Okay. About this topic, Wildan, I suggest you to have a look to the last webinar we had by Professor Scasso, who talked a little bit about petroleum system and volcaniclastic sedimentation. So I think that it has been a really good afternoon, okay, with you, Duje. Thank you a lot for your great presentation. Very, very nice. And I would like to thank everybody who participate to this talk. And if you lost something, if you arrived in late, I will upload the talk on YouTube. Sorry for my conversation that went away for a bit, but I will put everything on YouTube. Okay, so follow us. We will have other talk. One will be by Kyoto Kataoka, let's say in mid-October. She will speak about Japan and volcaniclastic activity and how to reconstruct source to sink systems. Then we will have in November, end of November, Sebastian Watt, impact of lahar on submarine systems. And then at the end, we will have two colleagues from the Commission, Manuel Lopez and Leandro Delia, that will talk a little bit about their work on volcaniclastic and volcanic activity in Southern America. Okay, so thanks again, Duje, for having this great talk, and see you next time.
Yeah. Take care. All the best to all of you. Bye.
Bye-bye.